Let's begin with this example. Let's find a basis for the kernel and image of A. Well, we have practiced this kind of thing, this new language that we discussed last video of the basis, but here we go. The first thing we need to do is transform A into reduced row echelon form. So I will take -3 row 1, add it to row 2, and then minus row 1, add it to row 3. This is our first step. Let's see what we get. Row 1 remains the same. Row 2, well, this is, we take -3 times this, add it here, 0, 0, 0. Oh, goodness, 0, 0. Okay, well, that's row 2. And now we take minus row 1, add it to row 3, 0, 0, then we get 1, minus 1, and 1. We know in reduced row echelon form, we must have, if there is a row of zeros, it has to be at the bottom, so I will interchange row 2 and row 3. I will interchange row 2 and row 3, and then I'll recopy over here. 1, 2, 3, 2, 1. We get 0, 0, 1, minus 1, 1, 0, 0, 0, 0, 0. Now we almost have reduced row echelon form. Leading 1, there's zeros below here, though we need to have a 0 above. And then we will be in reduced row echelon form. So there will just be one more step here where I take -3, row 2, add it to row 1. Oh, I flipped the colors of my caps. Row 3 remains 5 zeros. Row 2 remains, and then row 1 is 0, 1, 2, 0. And I take -3. This turns that into a +3. Here we get a 5. And then -3 plus 1, -2. This is in reduced row echelon form. And once we have transformed a matrix into reduced row echelon form, we can find a basis for the kernel and the image. I will start with the image. It's a little easier. We look in the columns here where we have leading ones, and we pull off the columns, or the corresponding columns out of the original matrix. Oops, okay, so the image of A is the span. Well, in fact, what I'm writing is a basis, but I will write it this way. We have the first column and the third column. This is the basis, and now I need to answer the same thing about the kernel. My free variables are here. This one's free, this one's free, this one's free. And so let's see, if I set x2 to be P, x3 to be, no, that one's not free, x4 to be Q, and x5 to be R, what I have is that x1, if I move this over there, this will be -2 P, -5 Q, and then +2 R, and x3, if I move these over here, will be, let's see, it's going to be in terms of x4 and x5, it'll be Q minus R. Okay, so now we can write what a general vector in the kernel looks like with these 3 letters. I'll put it here. Oh, I'm going to need more space than that. Well, I have minus 2p minus 5q plus 2r, and then x2 is p, x3 is here, q minus r, x4 is q, and x5 is r. Okay, well, I'm still not finished. I want a basis. So what I do is I just break this into 3 vectors based on p, q, and r. So let's do that next. I may write this as p times, let's see, minus 2, 1, 0, 0, 0, plus q times minus 5, 0, 1, 1, 0, and then plus r times, let's see, 2, 0, minus 1, 0, 1. Okay, now where can I erase? Maybe I will erase some of this work. I'll keep my original matrix. I will erase some of this work just to write down the basis that we see, but I'm going to talk about it just a little bit. Okay, so I found this, and now I'll use this part of the board. So the basis, the kernel of A, is the span of these 3 vectors, minus 2, 1, followed by 3 zeros, and then minus 5, 0, 1, 1, 0. And finally, we have 2, 0, minus 1, 0, 1. In fact, it's more than just saying the span. I'm saying that this is a basis and that this is a basis. So maybe I should even write my answer differently. I'll just take this part off and just do this. Kernel A, do this. This is the basis. And the image of A, like this. This is the basis. That way, I'm making it clear that it more than just spans, that it's the basis, which means it spans and it's linearly independent. In this example, how do we see these 2 are linearly independent? Well, it's only 2 vectors. Neither of them is 0. This vector is not a multiple of this vector. They're linearly independent. How do we know that they span? You know, this goes back to our discussion from yesterday. Well, if you go back to your original matrix, I have now erased the reduced row echelon form, which is unfortunate. But where we have the free variables, these were the ones that we had the redundant vectors, meaning we could write them as a linear combination of these. And so this we have discussed, but this in fact is a basis. It's linearly independent and it spans, well, it spans the same set that the columns span, and by definition that's the image. We've done a little bit more with the image, but why? Let's talk about the kernel. Why do these 3 vectors span? Well, you see I left this down here on the board. We found over here, or maybe it was here, a general element in the kernel. Okay, and then I write it exactly like this, as a linear combination of these 3. And so that justifies that these 3 span the kernel. Okay, now maybe I'll erase this as I keep talking. But to see that these 3 are linearly independent, we could use some of the discussion that we went through last time, where you just look at your zeros. Suppose you had C1 times this plus C2 times this plus C3 times this equals 0, namely some linear relation among these 3 vectors. Well, that corresponds to, for example, 1, 2, 3, 4, 5 equations. The very last equation says 0, 0. It says C3 is 0. So now you know that's 0. And then if you look at this equation, this would say 0 plus C2 plus 0 is 0. So now this one's 0. And then if you look at the equation corresponding to this row, it would say that C1 is 0, right? So we did this a little bit in the last video. You can argue that a collection of vectors is linearly independent just by sort of looking at how the zeros are placed. So without a doubt, this is linearly independent, and then the way that I found these vectors, they span the kernel. So this is a basis for the kernel, and this is a basis for the image. Okay, now let's make one more comment because I'm going to come back to this later. We're going to get to today a really big theorem in linear algebra, and I alluded to it 2 videos ago even. But what we see here, if you take the number of things in the basis for the kernel, we have 3. If you take the number of things in a basis, or number of vectors, I should say, in a basis, and right now I can only say in this basis, but we will see momentarily, I will say some more things. So this basis has 3 things, this basis has 2 things. You add them up, and we get 1, 2, 3, 4, 5, the number of columns. And this, I've even, like I said, I mentioned it at the end 2 videos ago, and it's a very important theorem we'll get to today, and it's not by chance that we see this. Okay, well, this is a really nice, in some ways it's review, because we've been doing this where we take a matrix and we transform it to reduced row echelon form. From that form, we find vectors that span the image, and I was calling it before minimal spanning set or something like this. And then we also would find vectors that span the kernel, but in light of this new language, we're finding bases for these 2 subspaces. Now suppose W is a subspace of Rn. And now, let's say, also suppose we have V1 to VP, and let's say W1 to WM are vectors in W. Okay? If these vectors, V1 to VP, put a hat, are linearly independent, and if these vectors, W1 to WM, span W, then we must have that P is less than or equal to M. Okay, another observation or fact, really it's a theorem, but I'm not proving. Some theorems I prove and some theorems I don't, and I'm not proving either one of these. But another observation that I want to make, it's in the same kind of spirit as these 2, is that any basis for a subspace W of Rn has the same number of elements, or I should say the same number of vectors. So I mentioned the same, pardon me, number of vectors. Sometimes writing and speaking doesn't go so well together. But I mentioned, as I was starting to say, in the first example that we did, I said, well, we see 2 elements in this basis, this particular one, for the image of that matrix. But really, if you had a different basis for the image, it would also have 2, okay? So any basis for a subspace, you fix a subspace W, then any basis of that subspace will have the same number of vectors, and this has a name. It's called the dimension. So definition, the dimension of a subspace W in Rn is the number of vectors in a basis for W. Okay, well, let me tell you one little technicality that I don't know if it's a technicality or if it's a convention, but I will just say note, okay? Oh. The dimension of this, and this is the notation for dimension, it's dim, whatever the subspace is. The dimension of the zero vector space is 0. One way you can think about that is how would you even get a basis for this? Well, you certainly can't put 0 in a basis. 0 alone as a vector is linearly dependent. Basis is the empty set. The dimension of the zero vector space is 0, and then we can also comment, although I will mention why, that the dimension of Rn, well, what do you think? The only thing that makes sense is that it is n. If it was anything else, then this wouldn't make a lot of intuitive sense. The dimension of Rn is n. This blue is brand new, but it's very light. I'm not sure I'll use it. But how could we see that in light of this definition? Well, we can just take this These are the standard vectors. This is a basis. Now, why is that the case? Well, technically, I need to show they are literally independent and they span. So if I have any x1, x2 to xn, I can definitely write this as a linear combination of these standard vectors. This is just x1, e1 plus x2, e2 plus xn, en. Okay, so this argument shows spanning, and then why is this collection linearly independent? Well, we talked about that a lot last time, but if you put these vectors in a matrix, we get the identity. Like sometimes people put big zeros. This is the identity. If you put these as columns in a matrix, and this, the kernel of this matrix is 0. And this says that the vectors, the columns, are linearly independent. I will abbreviate linearly independent. This is one of the ways we discussed last time. But also you could just take some linear relation, C1, E1, C2, E2 to Cn, En, and because of the fact that where the zeros are placed, you would conclude that all the Ci's must be 0. That was another characterization of linear independence. In any case, these standard vectors in Rn are linearly independent and they span, and this gives us that they are a basis for Rn, which means we know the dimension of Rn is n. Okay, let's consider this subspace in R3 that's given by just z is 0, the third coordinate is 0, and we can think about this geometrically. It is a plane. Well, it's the xy plane with z equals 0, so sitting inside R3. This is z. Okay, well, I have these different groups of collections of vectors because I want to make some comments. So all the ones up here, these are all linearly independent. And I will also say, unless I made a mistake, I don't think I did, every vector you see on the board is in fact in this subspace. Okay. First, when I was drawing, I put a 1 here. I was like, no, not in the subspace. But everything on the board is a vector in the subspace, and then I have them in collections. All of these, so this collection is just one vector. These two, this one, these two. These are collections of linearly independent vectors. And down here, these are collections of vectors that span. Okay? And I could have kept going and made many, many more examples of ones that span or of ones that are literally independent. But what I'm trying to point out in this is that you notice, let's count how many are in the sets. I have one vector, two vectors, one vector, two vectors. Okay, here, that's literally independent. To be spanning, I have 2, 4, 2, or I could have made ones with 3, 8, 10, 15, whatever, okay? That the dimension here is 2. Of this subspace is 2. This collection, well, you see it both. It is spans and is independent. You see in both, this forms a basis. This one forms a basis. It's independent. I could have also listed in the spanning one. Not a basis, because it doesn't span. Not a basis, and not a basis. These are definitely not literally independent. Okay, but my comment is that you notice the collections that are literally independent have less than or equal to 2 elements, and the collections that span have greater than or equal to 2 elements. And this holds generally, so let me write that. And the nice thing about this, well, we get a nice fact sort of from this, I'll say that. Okay, so my comment on this, or you could say it's a theorem. Suppose W is a subspace in Rn, and we know the dimension. The dimension of W is, M. Okay. Then, there's 2 things here. First, any spanning set must have at least M vectors, and similarly, any collection or any set of linearly independent must have or will have no more than M vectors. And we saw this in the example, but it's true in general. And one very nice thing about this is, if you know the dimension, maybe I will put red stars around this. If you know the dimension of a subspace that you are interested in, happens to be some M, okay? Then, well, just as here I had 2 things, I will have 2 things to say here, but any collection of M vectors in W that span is a basis. And any collection of M linearly independent vectors and M, yes, and W is a basis. So the nice thing about this, okay, spanning vectors that span, you know the number, it's got to be at least as many as the dimension, okay? Vectors that are linearly independent, it's got to be no more than the number of, or the dimension, okay? So if you're in this really happy place where you know, for instance, that your vectors span and you have exactly the dimension of your subspace, this will be a basis. That's the first part. And similarly, if you're in the other really happy place where you know the dimension of your subspace and you have a collection of that many vectors that's linearly independent, it's a basis. So you don't have to, if you know you have the right number, you don't have to check both independence and spanning to conclude you have a basis. Okay, this is the nice thing about this. Now let's do an example that uses this. I'd like to show that this collection of 4 vectors forms a basis for R4. Okay, so we have the right number, right? I have 2 options. I can either show it spans, which means I need to be able to just take some vector in R4 and write it as a linear combination of these. Or I can just show that these vectors are linearly independent. And because I have the right number, 4 and 4, I don't have to do both to justify that I have a basis. So I'm going to just show they're linearly independent because we have all kinds of things we can do. So let's show they're linearly independent. In particular, one thing I can do is I can just make a matrix with these as the columns, and then if I have that the kernel of the matrix is 0, I know the vectors are linearly independent. This was one of our characterizations of linearly independent vectors. Well, you see, I'm actually not that far away from reduced row echelon form because I have this whole part right here. It looks like a little identity, but I need to take care of this bottom row. So I will maybe do several things in one step. I'll take -2 row 1, add it to row 4. I'll take -3 row 2, add it to row 4. That would be this one. And then I'll take -4 row 3, add it to row 4. This is going to give me 0, 0, 0, right? And this is my goal, trying to get this matrix to reduce row echelon form. What do I have next? Well, I'm not touching the first 3 rows. Okay, and then here I get 0, I get 0, 0, but now I have to think about this entry. It's going to have -2 times 2. Maybe I should write this as a little side work. This bottom entry will be -2 times 2, -3 times 3, -4 times 4, which gives me -29. Okay, so this entry here is -29. Well, you see what's going to happen after this, because what can I do if I want to really go all the way to reduced? So first of all, this is in row echelon, it's just not reduced. But to get it in reduced row echelon form, I would just multiply -1/29 to row 4. But then once I have a 1 here with all these zeros, I could just multiply -4 times this row, add it here, -3 times this row, add it here, -2 times this row, add it here, and I would eliminate all of the numbers above. So I'll just put that, I said it, I'll put ... because we can see right now what the reduced row echelon form will look like. It is going to be this 4x4 identity. This says that the kernel of this matrix the original matrix is just 0 because we have no free variables. We have a rank 4x4 matrix. And so this says that the vectors are linearly independent. So we have a linearly independent collection of 4 vectors in R4. They form a basis. These vectors form a basis. for R4, because we have the right number. Now, one thing that we saw from this example, well, it's another characterization of when an n by n matrix is invertible. This is something that we had many ways to say, and I'll come back at the end of this and go over all of them again, or mention them at least. So we saw another characterization for a matrix to be invertible. A matrix is invertible if and only if the columns of A form a basis for Rn. Okay, because they're n by n, there's n of them, n are n, and it's invertible. Well, one of the several we saw is that the kernel is 0, and this is another way to say, as we saw in the last example, lots of different ways to say a matrix is invertible, but this new one is that the columns of A form a basis for Rn. Very nice. Well, what I want to move toward now is one of I don't know if it's the most important theorem in linear algebra, but it's huge, and it's the one that I have, like I said, alluded to in a few videos from this chapter, and we've been building towards this for the past couple of videos. It's called the rank nullity theorem. I'm going to state it more than one way. I'll first state it in terms of what we've been thinking about, then I will rephrase it. So suppose A is n by m matrix. Okay, this theorem says the following. The dimension of the kernel of A plus the dimension of the image of A is the number of columns. Well, I even talked about that in this first example before I even had defined dimension. And I talked about this or mentioned it 2 videos ago at the very end, and I hadn't even defined linear independence. But we had gone through the procedure, really, of finding a basis for the kernel and finding a basis for the image in that video. So today we saw one where it was what? 2 plus 3 equals 5, okay? And then 2 videos ago we had 2 plus 2 is 4. But this is generally the case. And if you really go back to how I talked about it before, this is the number of columns. And once we move to reduced row echelon form, every single one of these m columns either has a leading 1 or corresponds to a free variable. There's another way to say this. You notice I haven't used the word rank or nullity yet. So the other way to state this exact same thing, quite often the dimension of the kernel of a matrix is referred to as the nullity of A. And then this is just translated to say that the nullity of A plus the rank of A, we know these two are the same. In fact, the rank is the number of leading ones, and each one of those corresponds to a column you pull off of the original matrix to get an element of the basis for the image. Okay, this equals M. So this is the rank nullity theorem, and it's quite powerful. You can say all kinds of things, not only about matrices, but about linear transformations using, well, it's just an equation. Let's use the rank nullity theorem in a few examples. Okay. In this one, suppose we have a linear transformation from R5 to R3. The question is, what are possible values for the dimension of the kernel? Well, okay, here we go. What do we know? If you have a map, linear transformation from R5 to R3, you have a corresponding matrix A. This is the matrix for the transformation. And this will be 3 by 5 because, well, it always works this way, but if you want to check, T takes in something in R5, and when you multiply by A, this will also take something in R5 and produce something in, the middle ones match, 3 by 1, and this produces something in R3. Okay, in any case, this is the size of the matrix for T, and we know, well, let's write down the theorem, the rank, I'll write it this way, of A plus the dimension of the kernel of A. The kernel of T and the kernel of A, as we discussed last video, they're the same. This will be the number of columns of A, which is 3 by 5, is 5 columns. Okay, but we can't just have every possible thing because there are restrictions on the rank. We cannot have more leading ones than we have columns, for example, or more leading ones than we have rows, because you can only have, I should say, at most one leading one per column or per row. So we know that the rank of A must be less than or equal to whichever number here is smaller. It's 3. So now let's write down the possible, or the possibilities that we get. We could make a little chart even. Okay, this will be fun. Well, if we have a given rank, what would the corresponding dimension of the kernel be? But not with this one. This is my better blue. So the rank must be less than or equal to 3, means it could be 0, 1, 2, or 3. You could have a matrix with rank 0. That's just the 0 matrix, and the corresponding map would be the 0 map. That certainly can happen. Rank is 0, the dimension of the kernel is 5, this would be 4, this would be 3, and this would be 2. So this is the answer to the question. The possible values for the dimension of the kernel of T are all of these numbers. Now, what does that give us, or why is this interesting? In particular, what we can see from this is that T cannot be what's called 1-to-1. Okay. This is kind of, you've seen it, it's kind of analogous functions between finite sets. You might remember if you have a finite set with 5 elements and a finite set with 3 elements, you can't have any 1-to-1 maps that go from a finite set of 5 to a finite set of 3. And it's a similar statement here, even though both of these are infinite sets and T is a linear transformation, but we cannot have any 1-to-1. T cannot be 1-to-1 because you see the kernel is going to have at least dimension 2. In this case, we have a linear transformation. It goes from R4 to R7, so we're mapping into a bigger dimensional space. And we want to know the possible values for the dimension of the image. Okay, well, let's write down the matrix. A here would be 7 by 4, right? It takes in something from R4, it gives you something in R7. And then we know that the rank of A must be less than or equal to 4. Well, actually, in this example, I don't even need, the rank nullity theorem. It would say that the rank of A, or maybe I'll write it in terms of the dimension of the image. It would say the dimension of the image of T plus the dimension of the kernel of T is the number of columns, 4. But as I realized, I'm not going to even need that because this here is already this, right? The rank of the matrix gives us the dimension of the image of the transformation. And so the possibilities we can have for this, well, this can be 0, 1, 2, 3, and 4. And so what we see here in particular is that this cannot be on 2. And onto just means that, so in other words, the image of T is not going to be equal all of R7, right? Because this is the most it can be in dimension is 4 dimensions, and R7 is 7 dimensions. 7 is bigger than 4. So this is a similar statement. Again, if you've seen something similar with just functions between two finite sets. If I had a finite set with 4 elements and another finite set with 7 elements, I would not have any onto maps from the set with 4 to the set of 7. It's different in that these are both infinite spaces, and T is a linear transformation, but it's similar in feel to that kind of statement. Now let's do another one, and this one is similar to one you have in your homework. I will say this, but is also similar to one that we did in the last video. Well, in the last video, we did this really neat example kind of near the end. And it said if you have, let's see, n by m matrix A, and you have an m by n matrix B, and m is not equal to n here. And then with A, B is the identity, this n by n identity, then we proved the columns of B are, let's see, linearly independent. We proved this last time. Okay, well, let me change this a little bit. Well, first, before I change it, let's do an example of when this can happen. And I called this a left inverse. A is a left inverse of B. Okay, well, let's do an example of when this could work. Let's take something simple, perhaps. Okay, so here A is going to be 3 by 4, and B will be 4 by 3. Uh-oh, I don't want to leave that off. Here's A, and here's B. And what do we get when we multiply? Well, definitely we get something 3 by 3. And if you check, here we get 1, we get 0, 0, then second row, first column, 0. Then we get 1, 0, and finally 0, 0, 1. Okay? So this is an example of the type of thing or would be covered in the proof we did last time. And you notice, in fact, the columns of B are linearly independent. Okay, but I want to change this. My question is, can we have a, let's say 4 by 3 matrix A and a 3 by 4 matrix B with A, B is, in this case, it would be this 4 by 4 identity. This is a very nice question, right? It's related to what we did last time, but it also is going to use rank and nullity. Well, let's look at the matrix B. And then, first of all, I'm going to use this, but then also I'll think about it without this exercise that we proved. If we look at the matrix B, we know that the rank of B is less than or equal to 3 because, well, as I mentioned, you take the smaller of these two numbers and that's the maximum the rank can be. And then we know that we also have, maybe I'll write it below, the rank of B plus the dimension of the kernel of B has to be 4 because that's the number of columns in B. If this is less than or equal to 3 and this is 4, this means we can therefore conclude that the dimension of the kernel of B is bigger than or equal to 1. In particular, this says that the kernel is not just 0 because the 0 subspace we discussed has dimension 0. So if your dimension bigger than or equal to 1, it means that you have something in the kernel besides just 0. So this says that the columns of B are not linearly independent. If we use this, it says that, of course, we cannot find a matrix A and a matrix B such that AB is the identity, 4 by 4 identity here, because we could then conclude they're independent, but we know that the columns are dependent. They're not linearly independent. So the answer is no, because of what we proved last time, this observation. Okay, but without this, let's say we don't even want to use this that we proved. We want to understand why the answer is no. Another way, put a line, this was a new question, but the answer to this one is no. Okay, how could we see that? So now I have A, 4 by 3, we have B, 3 by 4, and because of this argument here, as the dimension of the kernel of B is bigger than or equal to 1, we may find an X not equal to 0 in the kernel of B. Okay? So like I said, I'm not going to use the theorem we proved last time right now. I'm going to use this part, which I already argued. The dimension of the kernel is bigger than or equal to 1. Use the rank nullity theorem. But now, what can I do from that? Okay, so what does that mean? This means Bx equals 0 and x is not equal to 0. Okay, so what happens when I apply AB to x? Well, AB, let's erase this example. It's no longer relevant to what I'm working on. I'm doing the other way. AB, x. Well, we can multiply this way. A, bx. And this is A, bx is 0. Any matrix times 0 gives you 0. This is 0. Well, this, if I want to put parentheses, would be like this. So what we see is that x is in the kernel of A times B. So there's no way that this is the identity. Because, while the identity is rank 4, the kernel is 0, right? Okay, so this is another way to see that exact same thing, that the answer is no, without quoting a theorem that we proved last time. And in fact, if you know something about sets, what we showed here, really what we showed is that the kernel of A, B, let's see, no, it goes the other way. The kernel of B is a subset of the kernel of A times B. This has nothing to do with them being 3 by 4 or 4 by 3. This is very general. If you know something about this, you know how do you show one set as a subset of the other, where you take an element in here, right? X is in kernel of B, and then you show it is in here. And that argument worked in general. So just as a comment, I'd like to end this video and end our discussion of chapter 3 kind of in a way that we have ended before, and it's been a theme this whole chapter of different characterizations of being invertible. And this comes out of the text. I have screenshotted it from the text, but what we added this time, let's see, was 7, 8, and 9. Some of the ones I had before are not listed because they were in terms of the transformation, and they're equivalent to ones here. But we have an n by n matrix A is invertible. It says the linear system Ax equals B has a unique solution for all vectors B. That's equivalent to saying that the reduced row echelon form of this n by n matrix is the identity, or that the rank is n, or that the image is all of our n. This was the onto, or that the kernel of the matrix is 0. This would say that the transformation is 1, 2, 1. All of those we had discussed, but the new ones today, that the columns, vectors of the matrix form a basis for our n. And then we know, while you have n columns, those are going to be a basis provided, well, all you need to do is check that they span. Because you have the right number, you would have a basis. Or the last one, all you would need to check is that they're literally independent, and you have the right number, then you would have a basis. So this is called Summary 3.3.10 in the book. It really summarizes a lot we have discussed in this chapter, and I figured it would be a nice way to close out our discussion in chapter 3, is to sort of come back to this theme.